Okay, in this video I'm going to take the Logic Quiz 2 practice quiz. So this quiz is on Unit 2, Mods 2 and 3, so it includes translations and truth tables. Question number 1. Using the key provided, select the correct translation of the following compound statement. So full process. Step 1, identify operator words, negation. Here's a conditional. Here's an either or, this goes together. Double check for negations, those are the easiest things to miss. And then identify atomic statements. So I don't study zoology. Atomic statement, I do study zoology. If I study either botany or astronomy. So I study botany and I study astronomy are the atomic statements. Now let's walk through the partial translation. So I don't study zoology if I'm seeing that this is main operator conditional, and I'm just going to rephrase it so it's if blank then blank. Whatever comes after the if is the antecedent, unless there's an only if, that's a special case. Whatever comes after an only if is the consequent. So if either I study botany or I study astronomy, so if B or A, then the other part will be the consequent. I don't study zoology, so not Z, which is B or A, horseshoe, not Z. Now, let A and B have the truth value T. Let Z have the truth value F. Given this assignment of truth values to the atomic statements A, B, and Z, what is the truth value of the above compound statement? So the above compound statement, let's start there, was B or A, then not Z. Now what's the truth value of this whole statement? Is this statement true or false? Well, it depends on whether or not B, A, and Z are true or false. And say we don't know, but we are stipulating, assume, that B and A are both true and that Z is false. Then, given those stipulations, what's the truth value of the whole statement? So a disjunction is true when both parts are true. And the negation of F is T, which leaves us with the conditional if T then T, which is true. The only time a conditional is false is if the antecedent is true and the consequent is false. So final answer, T. Say we want to set up a truth table for the compound statement from question 1. So again, that's this one. How many atomic statements, rows, and columns will be required? Well, how many atomic statements are there? Just count the number of different letters, A, B, and Z. So that's 3. How many rows will you need? This, just have memorized. 1 atomic statement equals 2 rows. Why? Because our goal is to figure out how many possible truth values there are. If you only have one statement, it's either true or false. So we'll have a row for when it's true and a row for when it's false. 2 atomic statements equals 4 rows. Why? Because when there are 2 atomic statements, there are 4 possible combos of truth values, TT, TF, FT, and FF. And when you have 3 atomic statements, there are 8 possible combinations of truth values, so you're going to need a row for each of those, 8 rows. So the minute you know how many atomic statements are, you know how many rows you'll need. How many columns are required? Well, that depends on the statement. So we know we're going to need one for each of the atomic statements. We know we're going to need one for the whole statement, the final thing we're interested in. And we know we need columns for all of the parts. So we're going to need a column for B or A. And we're going to need a column for not Z. And we'll need columns for all their parts. Well, their parts are atomic statements. So they're already in the table. So final answer, how many do we need? 1, 2, 3, 4, 5, 6. The next 2 multiple choice questions are asking about whether or not the table is set up correctly. So you're essentially looking for errors. And I recommend before even looking at the options that maybe think about the setup in your head first. So here's the thing we're making a table for. It's our last column, so we're trying to get a table for this. How many atomic statements are there? A, B, and Z, 3 different letters, so that's 3 atomic statements, 8 rows. Do we have 3 atomic statements? No, we've only got 2. Do we have 8 rows? No, there are only 4. So we can definitely see there's already problems. Are all the columns present? Well, we have a column for the whole thing. We have a column for the first bit, the antecedent, and the consequent. A and B are both in the table, so those parts are, but Z isn't. So we're only missing the column for Z. Okay, let's look at what our options actually are. All atomic statements are present. No. Atomic statements are in alphabetical order. The ones that are given aren't even in alphabetical order. It has the correct number of rows. No. It has the correct number of columns. No, it's missing Z. How about E? The order of the columns 3 through 5 is acceptable. What is the rule for column order? There's only one rule, and that's parts come before wholes. So this has 2 parts, B or A and not Z. That's columns 3 and 4, and they come before the whole, 5. And their parts, if we were concerned about going further, should be before wholes. But 3 through 5 is acceptable. Okay, let's look at our next table. So before I even look at any of this, let's look at what we're given. We've got a statement, same one that's right here. How many atomic statements are there? Well, 2 different letters, C or D, and they are in the table, which means we should have 4 rows. Check. Are all the columns present? Well, we've got the column we're interested in is in the table. It has a part not C, that's in the table. It has not C or D, that's in the table. Are all their parts in the table? Well, not C has part C in the table, and this has parts not C and D. Yes, so all the columns are present. So far, everything is looking good. All atomic statements are present? Yes. Alphabetical order? Yes. Correct number of rows? Correct number of columns? And is the order of columns 3 through 5 acceptable? Are the parts before the wholes? Part, whole. Yes. Construct a truth table for the following statement. Step number 1. How many atomic statements are there? There's X and Y. So we can immediately set up the table, leave lots of space for the columns part, and we can get straight to filling in the truth values. We know that there are 2 atomic statements. We don't know whether they're actually true or false. We just know that there are 4 possibilities. So we'll fill them in, top half T's, bottom half F's, and then alternating. So we get TT, TF, FT, FF. And it's important to do it in this order, not logically. Logically, all that matters is we have figured out the truth value for every combo. But for auto-grading purposes, it's important to fill them in this way. Okay, now we want to get all the columns in. So our final column is going to be the whole statement. And all that's left is to make sure all the parts of the statement are in the table, because in order to figure out the truth value for this conditional, we need to know the truth value of the antecedent and the consequent, which means those both need to be in our table. X is already in the table, so that's covered. What's not in the table is not X and Y. Now, its part is the conjunction X and Y. In order to figure out the truth value of this statement, we need to know the truth value of this one. So we're going to put its part, X and Y, into the table. And its parts are just X and Y, which are already in the table. So this is set up. We can now fill in the truth values for each of the columns. So column here, this is a conjunction, which means we need to look at the columns for its parts, its conjuncts, and that's the atomic statements X and Y. The only time a conjunction is true is when its conjuncts, its parts are true. So let's look at all of the rows. Here's one. No, no, no. So we can immediately put in F's for the other parts. Now we are looking at the negation of x and y, which means we need to look at the column for x and y. Wherever x and y is true, not x and y is false, and vice versa. Next, we are looking at a conditional. A conditional truth value depends on the truth value of its antecedent and its consequent. So we need to look at the column for the antecedent, that's this one, and the consequent, that's this one. One thing we might do is make it super clear which column is the antecedent and which column is the consequent, because order matters. So I'm going to highlight, so this is the antecedent, I'm going to highlight this one in green, and this is the consequent. And it's not the order in the truth table that matters, it's the order of the conditional that matters. So the only time a conditional statement is false is when the antecedent is true and the consequent is false. So let's look at rows where the antecedent is true and the consequent is false, if there are any such rows. So no, here it's true and true, so no. Here it's true and false, here's one. True and false, here's one. So these are the cases where the antecedent is true and the consequent is false. In every other case, the conditional has the truth value t, true. And that completes the truth table. Let's construct a truth table for this statement. How many atomic statements are there? Well, there's only one letter, P. Not P is not an atomic statement. It is the negation of P. What are the possible truth values P could have? Well, it's either true or it's false. That's it. Now we're going to need to leave some space for the columns. We want to make sure that the whole statement we are interested in is in our table. And we need to make sure every part is in the table. The first disjunct P already in the table. How about P and not P? We need to make sure that is in the table. Its parts are P in the table, and not P, we need to add not P to the table. Okay, so now that we have the table set up, we can fill in the truth values. Not P is the negation of P. Wherever P is true, not P is false, and vice versa. The conjunction of P and not P, we need to look at the columns for the two conjuncts. The conjuncts are P and not P. A conjunction is true only when both parts are true. So on either row, are both parts true? No. So there's no row where this conjunction is true. It'll be false on both of these. Next, we are looking at a disjunction. So we need to look at the columns for its parts, its disjuncts, and that is the column for P and the column for P and not P. A disjunction is only false when both parts are false. On row 1 we have TF, on row 2 we have FF. So it's going to be false on row 2, true otherwise. And that completes the table for this statement. So when you're asked to construct a truth table for a single statement, the goal is just to figure out the possible truth values of that statement. When the atomic statements are, in this case P is true, the whole thing is true. F, the whole thing is F. Similarly, this tells us what are the possible truth values for this statement. Well, it depends on the truth values of the parts. If the parts are both true, the whole thing is true. If X is T and Y is F, still true. But if X is F and Y is T, well then it's false. And if they're both F, also false. So the goal is just to tell us the possible truth values for this statement. The other kind of question we have is about relationships between sets of statements. So for question 8, consider the joint truth table for the following set of statements. A joint truth table is exactly the same as the kind of truth table you just set up in the previous questions. The only difference is we want to put more than one statement in it. So to set this one up, It's set up for you, but to set it up, you would go through exactly the same process. How many atomic statements are there? Well, how many different letters are there? 2, A and B. So we put A and B into our table. We immediately leave ourselves a really long space. We fill in the possible combos of truth values for A and B, T, T, F, F, T, F, T, F. And then we make sure we get all of the statements of interest into the table. So statement of interest 1, 2, 3, 4 are all here. And we make sure that all of their parts are in the table. Well, this just has atomic statements as parts, and likewise this one, so those are in the table. This one's part is A or B, that's already in the table. And this one's parts are not A and not B, and those are in the table. So every statement of interest and its parts is in the table. Once we have a table for the multiple statements we are interested in, we can ask questions about relationships between those statements. And we're focusing on just a couple, equivalence and implication / joint implication. So equivalence. Are statements 1 and 3 equivalent? Well, here we are looking at statements 1 and 3. Are they equivalent? Do they have the same truth value no matter what the truth values of its component parts, its atomic statements are? For every assignment of truth values to the atomic statements, these two statements have the same truth value. That's the definition of equivalence. More simply, just on every row, is it the same? And this one is clearly no. There's a row where one is T and one is F, so they're not equivalent. How about 3 and 4? Notice that on every single row, they have the same truth value. So the answer is yes. They are equivalent. And let's use a simple example to illustrate why that is. Let A be, I have an apple, and B be, I have a banana. Statement 3 says, I have neither an apple nor a banana, not either. That means I've got none, right? If I have neither an apple or banana, then I've got none. This one says, I don't have an apple, and I don't have a banana. So again, you've got none. They mean the same thing. They are true or false in the exact same conditions. If you in fact have an apple and a banana, well then those statements are false. If you have an apple, while saying you have neither and saying you don't have an apple and don't have a banana, both false. If you do have the banana, again, same reason. This one said you had neither and this one said you don't have either. And they're only true when in fact you've got no apple and no banana. Then to say you have neither is true, and to say you don't have one and you don't have the other is also true. They're true or false in the same situations, same rows. Implication. Does statement 1 imply statement 2? What are we looking for with implication? So does statement 1 imply statement 2? Let's make the green be the doing the implying and the orange be the thing that's supposed to be implied. We are looking for, is it possible that 1 is true and yet 2 is false? The TF case. If you find the TF case, no implication. If there's no TF case, then 1 does imply 2. So is there any row where 1 is true and 2 is false? TT, irrelevant, irrelevant, irrelevant. So no TF case, which means yes, implication. Does statement 2 imply statement 1? Is there any row where statement 2 is true and yet 1 is false? Not on this row. Yes, yes. Okay, so the fact that there is at least one row, in fact 2, but that doesn't matter, that there's at least one row where 2 is true and yet 1 is false, that means no implication. And let's use our common sense sort of intuitive example to explain why this is. 1 says I have an apple and a banana. Does that imply that I have at least one? Yes. Alternatively, assume that I have either an apple or a banana. Does that imply that I have both? No. Does statement 3 imply statement 4? So does statement 3 imply statement 4. Is there any row where 3 is true and 4 is false? Well, they have the same truth value on every row, so there's going to be no TF row, which means, yes, statement 3 implies statement 4, and vice versa, 4 implies 3. They're equivalent. If one is true, the other has to be true. It's impossible that one is true and the other is false. So one equivalent statement applies any statement that it is equivalent to. Okay, joint implication. Do statements 1 and 2 jointly imply 3? The only difference between implication and joint implication is that more than one statement does the implying. So here we're going to look at statements 1 and 2, and do those statements together jointly imply statement 3. So is there any row where 1 and 2 are both true, and yet 3 is false? Well, right away on the first row there is such a case. So no. 1 and 2 do not jointly imply statement 3. Do statements 3 and 4 jointly imply statement 1? Do statements 3 and 4 jointly imply statement 1? Is there any row where 3 and 4 are both true, irrelevant, 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 here's one, and yet statement 1 is false? Yes. So 3 and 4 do not jointly imply statement 1. Finally, do statements 1, 2, and 3 jointly imply statement 4? So 1, 2, and 3, do they jointly imply 4? Is there any row where 1, 2, and 3 is true? So irrelevant, 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 irrelevant. There's no row where they're all true. What does this mean? Well, it means there's going to be no TF case. If there is no row where the things doing the implying are all true and the thing implied is false, then yes, 1, 2, and 3 jointly imply 4. This is sort of a weird case, but this is intro logic, so we won't talk about why it's weird. We'll just say that what our definition of validity promises is that you'll never have true premises and a false conclusion. You'll never move from true premises to a false conclusion. That's all that validity guarantees. Okay, and our last sort of two problems, these go together, are translate an argument into symbolic notation and then construct a truth table to evaluate that argument. Okay, so recall, to translate an argument into symbolic notation, the translation requires that you put that argument into standard form and you provide a key. So it says use letters C and D. If you have neither a cat nor a dog, then you don't have a dog. You don't have a dog, thus, conclusion indicator, you don't have a cat. So let's let C be you have a cat, you do have a cat, and D be you have a dog. How many atomic statements are there? 2. So I can already see that this is going to be a 4-row, 2, whatever, truth table, but that's for the next question. What we're doing right now is just translating it into symbolic notation. So next we want to put it in standard form. One is, and I'm going to do it using partial translations, if you have neither C nor D, then not D, you don't have a dog. Premise 2, you don't have a dog. Conclusion, you don't have a cat. Okay, the only tricky one here is premise 1. So if neither C nor D, how do we translate neither nor? There's 2 ways. Not either, or both not. And as we saw earlier, these are logically equivalent. But let's just go with this one, not either, neither. So if neither C nor D, then not D. 2 not D, 3 not C. So the only thing required for a complete answer is that you have a key and you have the final translation in symbolic, in standard form. This is helpful for getting to the right answer. Next, construct the truth table to determine whether or not this argument is valid. So step number 1, how many atomic statements are there? 2, put them in alphabetical order. We already know there are going to be 4 rows, and we can fill in all the possible combos of truth values right away. And then we want to make sure that all of our premises and the conclusion are in the table and we label them. I like to immediately do negations after atomic statements. It doesn't matter as long as parts come before wholes, but that's how I tend to do it. So we've got the conclusion, and we've got P2 in the table, and all that's left is making sure we get P1 in the table, and it's more complicated and has parts. So we know that we're going to end with C or D, then not D. And we just need to make sure all the parts are in the table. It has parts not D already in the table, and not C or D. So next we'll put not C or D, and it's important that this little tilde is outside of the parentheses. And then its part is C or D, and its parts are just atomic statements. Okay, that completes the setup for the truth table. Now we just have to fill in the T's and F's. So to complete not C, we look at the column for C. Wherever that's true, not C is F, and vice versa. Not D, we're looking at the column for D. Wherever D is T, not D is F. For the disjunction of C and D, we've got to look at the columns for C or D, and the only time a disjunction is false is when both of the disjuncts are false. So that's nope, nope, nope. Here's one. Every other row will be true. Negation of C or D, we look at C or D. Wherever C or D is true, the negation of that is F. And vice versa. Finally, we have a conditional statement. The antecedent is not C or D. The consequent is not D. Notice that the columns for the antecedent and consequent aren't in the same order as the conditional. A conditional is only false when the antecedent is true and the consequent is false. So we're looking for the rows where antecedent is true and consequent is false. Nope, nope, nope. Here's a row where the antecedent is true, and on this row the consequent is also true. So there's no TF row. That means it's true on every row. There was no row where it would be false. Okay, we have filled in the T's and F's. Truth table is complete. Now we can use it to determine whether or not the argument is valid. In other words, do the premises jointly imply the conclusion? What are we looking for? We're looking to make sure there is no row where both premises are true and yet the conclusion is false. A problem row. So let's make sure we remove anything that is potentially confusing. What are we looking for? Here's the conclusion. Here are the premises. Is there any row where both premises are true and yet the conclusion is false? This is a TF. Here's a row where they're both true and the conclusion is false. So that's a problem row. Notice down here we have a TTT row. That doesn't matter. We're not looking for a TT row. We're making sure there's no TTF row. And since there is, this argument is invalid. Not valid, invalid. Why? Because there's a problem row. Because there's a row where the premises are true and the consequent is, or the conclusion is false. Last problem. First we translate, then we construct a truth table to evaluate. Okay, this one's long. First, Fluffy is either a 3-headed dog or an acromantula. Second, It's not a Norwegian ridgeback dragon. Third, if Fluffy is not a Norwegian ridgeback dragon, then he's not an acromantula. From these three premises, it follows that Fluffy is a three-headed dog. Okay, so these argument indicator words help us to figure out that. We've got three premises and a conclusion. That's pretty clear. And what are the atomic statements? Let's let D be Fluffy is a three-headed dog. Let's let A be Fluffy is an acromantula. And let's let N be Fluffy is a Norwegian ridgeback dragon. Premise 1. First, Fluffy is either a three-headed dog or Fluffy is an acromantula. So either D or A. 2. Fluffy is not a Norwegian ridgeback dragon. So not N. 3. If Fluffy is not a Norwegian ridgeback dragon, then he is not an acromantula. So I can see that this is an if-then statement. That's the main operator. And the antecedent is not N. If not N, then consequent not A. And conclusion, Fluffy is a three-headed dog. Construct a truth table and determine whether or not this is a valid argument. Steps. 1. How many atomic statements are there? I.e., how many different letters are there? We've got A, we've got D, we've got N, importantly in alphabetical order. When we've got 3 atomic statements, we automatically know there are 8 rows, there are 8 possible combos of truth values that these 3 statements could have. So let's fill it in the standard way. Top half T's, bottom half F's. Then we imagine sort of cut this in half. Top half T's, bottom half F's. And then imagine sort of cut that in half again. T, F, T, F, T, F. Okay, so that's our 8 possible combinations of truth values. Next, we need to make sure that all of the premises and the conclusion are in the table. We've already got the conclusion in the table because it's one of the atomic statements. I like to do, as I said before, the negations of atomic statements right after the atomic statements, and I can see that there are 2 in here. There's not N and not A. I'm not going to just fill all of them in, so I'm not going to include not D because we don't care what not D is. That's irrelevant. But I'm going to do not A, not N, and then I'm just going to go through and do the premises. So, well, not N was already a premise. Let's identify that. That's P2. Next, D or A. Its parts are atomic statements, so that one's ready to go. That was P1. And then finally, if not N, then not A. Well, its parts are already in the table, so this one's ready to go too. Not N, then not A. Okay, so this table is set up. All that's left to do is to fill it in. So when we are figuring out the value of not A, we have to look at the column for A. Wherever A is true, not A is false, and vice versa. So F, F, T, 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 T. For not N, we look at the column for N. Wherever N is true, not N is false, and vice versa. Next, we have a disjunction, and the parts are D and A. A disjunction is only false when both of the parts are false. So I'm going to look for those rows. This is TT, TT, TF, TF, FT, FT. Here they are, F and F. So the only time this is going to be false is in these last two rows. On every other row, that's going to be T. And our last column is a conditional statement. The antecedent is not N. The consequent is not A. And a conditional statement is only false when the antecedent is true and the consequent is false. So let's just look for the rows where the antecedent is true and the consequent is false. No, here's one. No, here's one. No, 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 no. So there's only two. And that was rows 2 and 4. Everywhere else, it's T. Now that it's filled in, we can determine whether or not the argument is valid. So let's highlight the conclusion, that is this column, and the premises are the last three columns. Is there any row where the premises are all true and yet the conclusion is false? Irrelevant, 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 irrelevant. Here's one. Irrelevant, irrelevant. Okay, so this is the only possibly relevant row. T, 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 and it's T. And that means this is valid, not because we found the TTT case, but because we did not find a TTTF case. Valid. Why? If the premises are true, the conclusion is true. It's impossible that these premises are all true and yet the conclusion is false. It's impossible because these are all the logical possibilities. So this is valid. Okay, and that is the end of our Logic 2 practice quiz.